The fundamental problem of coding information sources is that of finding compact codes for that source. We have seen that Macmillan's inequality assures us that any set of code words lengths achievable in a uniquely decodable code is also achievable in an instantaneous or prefix code. In the literature, instantaneous code is also known sometimes as prefix code. Therefore, we restrict our search for compact code. By compact we mean optimum code which have the average length which is the smallest. So we restrict the search for our compact code to an instantaneous code. Now we have seen that if we wish to construct an instantaneous code for a source S, then the average length of a code is always greater than or equal to the entropy of the source. We have also seen that in order to achieve this lower bound of entropy, that is the average length equal to entropy of the source, in that case this condition should be satisfied where the probability of source symbols of the source, that is Pi, should be of the form equal to 1 by r raised to alpha I, where r is the size of the code alphabet. And then by choosing your LIs equal to alpha I can get my average length of the code equal to the entropy of the source. We have also seen that in a special case like this, how to construct an instantaneous code. Now for a very general case where this condition is not satisfied for all i's, what we said that we could use Shannon's coding strategy. Shannon's coding strategy says that I can choose my LIs to be greater than or equal to log of 1 by Pi less than log of 1 by Pi plus 1. What it means that we choose Li which is the first integer greater than log to the base r of 1 by Pi. If I use this strategy and if I do the coding for the nth extension of the source, then we have also seen that we get this relationship. This relationship says that the average length of the code symbols per source symbol will always be bounded by this inequality. What this inequality says is that as n tends to infinity, I can get this value of ln by n as close as possible to the entropy of the source, and this inequality is in fact Shannon's first theorem or noiseless coding theorem. Now the question of the limiting value of ln by n is really of no relevance in the definition of compactness, because we have defined a compact code for a source S to be a code which has the smallest average length L possible if we encode the symbols from this source S one at a time. So the next question that arises is, how does one construct a compact or that is optimum code for a fixed source? So far we have not looked into any strategy for coding information sources except for the special case where the probabilities of the symbols are of the form 1 by r raised to alpha I. Now before we look into the design methodology of a compact code which is based on Huffman coding strategy, let us have a look at some simpler techniques in order to appreciate the coding strategies being followed in a practical case. So, with this motivation, let us take up the first coding strategy, that is popularly known as Fano coding. Fano code goes as the coding strategy for Fano code goes as follows. Given the source output symbols, you arrange this source output symbols in order of decreasing probability. Then the next step is basically to divide the symbols as well as possible into R equally probable groups. So, R is the size of the code alphabet which we want to use for coding. Now, each group receives one of the R code symbols as the first symbol, and the final step is this division is repeated per group as many times as this is possible. Let us try to use this strategy and understand it with the help of an example. I have a source here with 10 source symbols. The probabilities of the source symbols have been given to me in this column. So, you first thing is what you do is try to arrange this source symbols in the decreasing order of probabilities. Now, this has already been done in this first step. Next is to divide this group into R possible group. Now, as far as our discussion is concerned, for the next few classes, we will try to restrict our discussion to binary alphabet. There are two reasons for this. The first reason is it is easy for us to understand the concepts with the binary alphabet, and the next is in most of the time in the practical scenarios we always use the binary alphabets, but it is not difficult to extend the ideas to any other code alphabet of size R. So, for our discussion at the moment we will restrict ourselves to binary code alphabet. So, in our case we have to divide this list of probabilities into two groups because we are considering binary alphabet. So, the first thing is you divide this into two groups, this becomes half and this obviously is half. So, I divide this into two groups and I allot to each symbol, source symbol in this group binary symbols. So, this is the first group and this is the second group. So, for the first group I allot 0 0 and to the next group I allot all ones. So, this is the first step I have got. Now, I have got two groups. Now, let us consider the first group. So, if you look at the first group, this first group which I have, I can again divide this into half. So, when I divide them into half, I get two groups, each group consisting of only one source symbols, and so again you allot 0 and 1. So, we are through with this group. Now, we move over to the next group. When we move over to the next group, we have this is a group. Again, divide this group into two parts equally as far as possible. Now, it is very easy to do this in this example. So, I divide this into two groups, this plus this turns out to be 1/4 and this probability of symbol, if I sum them up, is again 1/4. So I divide them into 2 and I allot 0 0 to the first group and 1 1 to the next group. Once I have done this, I repeat this process for this group now. So when I repeat the process for this group, again I have got 1 8 and 1 8. So when I divide into half, I get this 0 and 1. So we are through with this group. Now we move over to this group again. Again this group has to be divided into 2 parts. So when I do this, I get this. I allot 0 0 1 1 1 1. Then this group I again divide into 2 parts. I get 0 1. I move over to this group. I divide into 2 parts. I get 0 0 1 1. Then I move to this group. I divide to 2 parts 0 1, and finally this group I divide 0 1, and this is the code words which I have got for this source symbols based on the Huffman coding strategy. Now if you calculate the entropy for this source, assuming that the source is IID, HS, that is identically independent distributed symbols, then HS turns out to be 2.88, and for this case the average length also turns out to be 2.88. Therefore the efficiency, which is defined as the entropy of the source divided by the average length, that is HS by L, turns out to be equal to 1. Now there are some difficulties when we are carrying out coding using this strategy. First difficulty is that it is not always possible to separate precisely the probabilities into equally probable groups. It was possible in this case because the probability of the symbols were very nicely behaving, but this may not be always possible. In that case the division should be as good as possible. The result can be various alternatives. Now if you look at this, these PIs are each of the form 1 by 2 raised to alpha I. So we could have used the strategy of our instantaneous code design which we have discussed earlier, and the result would be same. Now let us take a case where this is not satisfied, where it is not possible to equally divide the groups. In that case, what do you do? So let us take up one specific example for that. So I have another example out here. I have a source consisting of 5 source symbols, and the probabilities of the source symbols have been given here. I again assume that this source is IID, that is identically independent distributed. Now if you go by the Huffman's coding strategy, you have to divide this group equally into 2 parts because we are assuming binary alphabet. So in this case the best one way of doing is you divide this into 2/3 and 1/3. So there is no other way to do it. I could have done 1/3 and 2/3, that is also fine. We will see what happens that way, but for the time being let us assume that I divide into 2/3 and 1/3. I divide this into 2 portions, 2/3 and 1/3. I assign to the above group as 0 0, to below group 1 1. To this again I divide it into 2 parts, equal part. It is possible for me to do that because 1/3 and 1/3, so I get 0 and 1. Now I come back to this group, I have to divide this into 2 parts. Now again the division is not possible, so one strategy could be divided 1/9 and 2 by 9. So if you do that, I get 0 1 1. This group is done because there is only one source symbol out here, but here in this group there are 2 source symbols, so I have to again further divide it into 2 parts, and when I do this I get 0 1. Now this I will call it as code 1, and instead of this division process, if I had followed another one, for example if I had divided initially as 1/3 and 2/3, then I would get 0 1 1 1 1. This group I do not have to do anything because there is only one source symbol, and this I can divide it again this is unequal. No, this is possible, I can divide it into 2 half exactly. So 1/3 and this is also 1/3, so I get 0 1 1 1 and this group is done. Again here I have, and I can divide it as 0 1 1. I could have used a different strategy, I could have divided here like we did previously. So, but if I follow this strategy I get this, and then again I have to divide this group, and finally I get this value of 0 1. So these are two codes which we have got based on the Fano's coding strategy. Now how do you decide between these two codes is to calculate the average length for both of this. Now if you calculate the average length for this code 1, the average length turns out to be 20 by 9, correct? And average length for this code also turns out to be 20 by 9. What it means that efficiency for both this code 1 and 2 are the same. So it makes no difference which codes I use. Okay. Now next thing which I wanted to bring out with the help of this Fano's coding strategy was to look at what happens to the average length of a code when my source has been given and when I change the size of my code alphabet. So I have the source is a fixed source, the source symbols have been given to me, I have been given the probabilities of source symbols, and now I am asked to design a coding for this source. Now for coding I have to decide my code alphabet. Now let us look at what happens when I choose different sizes of code alphabet. So this again I will try to explain this with the help of an illustration. Let us look at an example. I have a source consisting of 8 symbols with probabilities of the symbols given as follows. This already has been arranged in the descending order, that is the first step which you should carry out while carrying out the Fano's coding. So let me assume that I want to study the effect of increasing the size of the code alphabet X. So let us take the first case of the binary. So if I take my first case of binary and following the same strategy which I just discussed, you can show that the code using the binary strategy is this. So when you are using the design for a binary alphabet, you have to divide them into 2 groups. That is why you see there everywhere the division is into 2 groups. Now let us move to the case where instead of 2 bits, 2 bits, let us use code of size equal to 3. Now when I have size of code size, that is code alphabet size of 3, then I arrange them again in the decreasing order of probabilities and divide this into 3 equal sections. So that is the best way, whatever the best way I can do. So one strategy which I have followed here is I have shown that I have divided into 3 groups like this. Once you divide into 3 groups, to each group you assign the code symbol. So we will have 3 code symbols because the size of the alphabet of the code alphabet is 3. So the 3 symbols which we have chosen for the code alphabets are 0, 1, 2. So 3 groups are being assigned as 0, 1, 1 and 2, 2. Now you move to this group, I do not have anything to do, so I directly assign, do not have to assign anything. When I move to this there are only 2 source symbols, so I assign 0 and 1 to this. Now when I move to the third group, there are 5 source symbols which are left out, so I have to again divide this into 3 equal groups, and when I divide this is one strategy which I can follow. I divide them into 3 groups like this, and again for this I don't have to assign anything, For this group there are only 3 source symbols, so I can assign them 0, 1, 2. And similarly, if I extend this argument to the code alphabet size 4, where my code letters will be 0, 1, 2, 3, to initially to start with I have to divide my source symbols into 4 groups. So I have divided into 4 almost equal groups, 0, 1, 2, 2, 3, 3. So for this I have already assigned this, there is no need to assign 2 to, I can assign 0 and 1, and now for this last group I have got 4 source symbols remaining with me, so I can assign 0, 1, 2, 3. And now if you look at the calculations of the average lengths which we get from these 3 codes, the entropy of the source is 2.64 bits per symbol, whereas the length for this code turns out to be 2.66. The length for this code is 1.83, and the length for this code turns out to be 1.45. So on the average you will find that the L keeps on decreasing, but these are now array code symbols per source symbol, and if you look at the efficiency, these are the efficiency values which we get for these 3 cases. Now another example which I would like to take and illustrate the concept of how the coding efficiency improves when I go for the higher extension of a source. So we have said that, we have proved that theorem, that is Shannon's theorem, but let us have a look at one particular illustration in order to understand the concepts which we have studied so far in a better way. So I take another example out here where I want to show the efficiency improvement by using the extension of a source. So let us assume that I have 2 source symbols given as S1, S2 with the probabilities of occurrence at 3/4, 1/4. Simple way of, for binary code I will have 0 and 1. The entropy of the source is 0.81 bit. The length, average length is obviously 1. This is a binary alphabet, so R is equal to 2, and the efficiency turns out to be 0.811. Now let us see, basically, is it possible for us to improve this efficiency by going for the higher extension of this source, and we will do that based on the Fanos coding strategy. Now if you use the Fanos coding strategy, the first thing is that I have to get the source symbols of my extension of the source. So in this case we will assume the second extension of the source. If I have the second extension of the source, these are the 4 new source symbols which I will generate from the second extension of the source, and if I assume that this source is IID, then I can calculate the probabilities of this new source symbols. This we have seen earlier how to do that. So I get my probability of the new source symbols, and based on the probability of the new source symbols I can design my instantaneous code which is based on the Fanos coding strategy. I divide them again into 2 groups, 0, 1, 1, then again 2 divisions, 0, and finally I get this code for the second extension based on the Fanos coding strategy. Now if you look at this, the entropy of this source was 0.81, the entropy for this source, because it is an IID, the second extension of this source will be just twice of this entropy, that turns out to be 1.622, and if you calculate the average length for this code will be 27 by 16. Now this 27 by 16, and if you take 1.622 divided by 27 by 16, you will get the efficiency of the code to be equal to 0.961. So what I wanted to bring forward was that by using the second extension of a source, I can improve the coding scheme of for the source based on a particular coding strategy. Now in this case it was possible for me to get this kind of improvement, but it is not always necessary that you could get this kind of large improvement by going just for the second extension. It may be possible that you may have to go for higher order before you achieve the efficiency which is ideally equal to 1. Now let us take one more final illustration before we go ahead with another discussion. So I have another example out here. I have source consisting of 3 symbols. The probabilities have been given. If I, based on my Fano's coding strategy, I can get the code here, I get my entropy of the source, and I get my efficiency equal to 0.97. Now this efficiency of 0.97 is already quite close to the expected or to the ideal efficiency which would desire, that is equal to 1. Now in this case, if we go for the higher order of extension for the source, let us take a simple example of second extension, and then there will be 9 source symbols from the second extension of the source, original source. You can calculate the probabilities of the new symbols out here based on the assumptions of IID, and then based on the Fano's coding strategy, we can get the code for this source, and if you calculate the efficiency, turns out to be 0.98. In this case again we see the entropy of the source is twice of this, but the average length comes out to be very close to the entropy of the source, that is 2.97 is almost equal to 2.92. So this example shows that if the efficiency is already very close to the ideal expected value of 1, then going for higher order may not improve very much. So when I go for the second order extension, I get an improvement of approximately 0.01. Let us have a look at the design of the compact instantaneous code for a given probability model for a source S based on a simple algorithm which was developed by Huffman. In literature, this is popularly known as Huffman coding. Huffman coding was developed by David Huffman, who was a student of Fano as a part of a class assignment at MIT. These codes are instantaneous or prefix code and are optimum for a given model, that is the set of probabilities. The Huffman procedure is based on 2 observations regarding optimum prefix codes. These 2 observations are: in an optimum code, symbols that occur more frequently will have shorter code words than symbols that occur less frequently. That is the first condition which any optimum prefix code should satisfy. Another condition which an optimum prefix code will satisfy is that in an optimum code the two symbols that occur least frequently will have the same length. Now, it is not very difficult to see that both these observations are true. Let us look at the first observation. If this were not true, and let us assume that there was an optimum code where the symbols that occur more frequently were assigned longer code words than symbols that occurred less frequently. If we had optimum code of that kind, then what that would mean is that on the average the code word length of such an optimum code would be always larger than if the conditions were reverse. Therefore, code that assigns longer code words to symbols occurring more frequently cannot be optimum. So, this is true. Now, it is not very difficult to see that the second observation is also true. To understand this, let us assume that I have a code C and there are two code words xi and xj which correspond to the two least probable source symbols. Now, if they do not have the same length, let us assume that one of this, that is xi, is larger than xj. Now, and let us assume that this xi, the code word, is larger than this code word by k bits. Now, if this code C is a prefix code, then xj, which is smaller code word, cannot be prefix of xi. What it means that if I remove this k bits from xi, if I remove the k bits from xi, then I will get a shortened code word for the source symbol corresponding to xi. Now, since xj cannot be a prefix of this code word, even on shortening it, this cannot be prefix of the new code word which I get after removing these k bits. And since both these code words correspond to the source symbols which are the least probable ones, this code word even after shortening cannot be a prefix to another code word existing in the code C. But what will happen that after I have removed this k bits from this code word xi, the average length of the code C, of this new code C which I will get after removing this k bits, will be smaller than the code with which I started initially, which consisted of xi xj with k bits in xi, more k bits in xi compared to xj. So, the new code which I get will be, on the average length of the new code which I get will be smaller than this. So, what it means that the new code which I get is now an optimum code, but this actually violates our original assumption that this code C was optimum. So, based on this argument, it is clear that in an optimum code the two symbols that occur least frequently will have the same length. Now, these two conditions we will prove them more mathematically little later on when we try to provide the justification of the optimality of Huffman codes. Now, Huffman code, beside these two observations, the Huffman code is basically based on one more observation or a simple requirement is added to these two observations. This requirement is that the code words corresponding to the two least probability symbols differ only in the last bit. So, this is the requirement which we add. Now, what we mean by requirement is that if we have gamma and delta as the two least probable symbols in an alphabet, and if the code word for gamma was M with the last bit 0, again we are assuming a binary alphabet. So, M denotes the code word binary string and the last code symbol in this code word is 0. The code word for delta would be M star M. Here M is a string of ones and zeros because we are considering binary code, and this star denotes concatenation. Correct? Now, this requirement really does not violate our two observations and leads to a very simple encoding procedure. Now, before we try to provide a formal proof of showing that Huffman code is really a compact code, let us try to understand a coding strategy based on Huffman. So, to do that, I take a simple example. I have a source, so we are looking for the design of a Huffman code. I have a source consisting of 5 alphabets. I have been given that these 5 source symbols occur with this probabilities, P1, P3 is equal to this. Pi is nothing but probability of source symbol Si, and entropy for this source, assuming its 0 memory source, is 2.122 bits per symbol. Now, if my Huffman code is really a very efficient code, I expect that my average length of this Huffman code should be very close to 2.122 bits per symbol. Let us look into that. The first thing for doing for coding using Huffman technique is to take the source symbols and order them in a decreasing order of probabilities. So, in this case S2 is maximum, so this will be S2 followed by S1. So, we have initial 5 letters of the source, arrange them into the decreasing order of probabilities. So, these are the probabilities which I get, and let us assume that finally I want to get the code words for this denoted by CSI. So, CSI denotes the code word for SI. I want to get the code words for these letters. Now, we will follow the simple strategy which we just discussed. Now, in this case for the Huffman coding, you look at the first, since we are considering binary alphabet, you consider first 2 lowest source symbols which have the lowest probabilities and combine them. So, this is 0.1, 0.1. So, these 2 source symbols will differ, they will have the maximum code word length and they will differ only by 1 bit, that is in the last position. So, if I assume that the CS4 will be equal to alpha 1 concat with 0 and CS5 will be equal to alpha 1 concat with 1, where alpha 1 is a binary string which I want to find out. What is that alpha 1? So, this is the first step I have. So, this let us call this a table 1.1, that is the initial 5 letter alphabet which I have got. Now the second step is to define a new alphabet S dash. This is your S, and now we define a new source alphabet S dash with a 4-letter alphabet obtained by combining this two source symbol S4 and S5. So this can be explained as follows. So now we define a new alphabet S dash with a 4-letter alphabet S1, S2, S3, S dash 4, where S dash 4 is composed of S4 and S5, which corresponded to the two least source symbols, corresponding to the two least probable source symbols occurring in the source. So S4 and S5 are at the bottom of the order. So I combine them and get a new source symbol that is called S dash 4. This new source symbol which I generate S dash 4 has a probability which is equal to probability of S4 and S5, that is equal to 0.2. Now once I get this new alphabet which is of a reduced order, again you order this new alphabet in a descending order to obtain table 1.2. So I get a table 1.2. This is the reduced 4-letter alphabet which I have got now. It consists of S2, S1, S3, S4 dash. S4 dash consists of my two original source symbols S4 and S5, and again I order them in a decreasing order of in decreasing values of probabilities. And let us call the code word for this will remain as it is, this will remain, correct, and S4 dash, the code word for that would be alpha 1, because S4 dash is a combination of S4 and S5. S4 had the code word which was alpha 1 concate with 0, and code word for S5 was alpha 1 concate 1. Therefore the code word for S dash 4 would be alpha 1. Now S3 and S dash 4 are the two letters at the bottom of the sorted list. If you look at this, this is a sorted list, S3 and S4 dash are at the bottom of the sorted list. Now again, going by the same strategy of Huffman coding, these two source symbols in this new reduced 4-letter alphabet will be, the code words for this will be the same except for the last bit. So CS3 would be equal to alpha 2 some string concate with 0, and CS4 dash would be equal to alpha 2 concate with 1. Now we already know the code word for CS4 dash, that is equal to alpha 1. So we can equate this to alpha 1. So if we do that, so we know this CS4 dash is equal to 1, therefore I equate the quantity, I get alpha 1 is equal to alpha 2 concate with 1, which means that going back substitution, CS4 is equal to alpha 2 concate 1 0, and CS5 is alpha 2 concate 1 1, because based on the previous observation. Now at this stage we generate a new source, again a new reduced source, and the new alphabet for that new source we call it as S double prime, that consists of 3 letters S1, S2 and S3 prime, where S3 prime is composed of S3 and S4 prime, because S3 and S4 prime were lying at the bottom of the sorted list. So, I take this together and the probability of this new source symbol which I generate S3 prime will be summation of PS3 plus that turns out to be 0.4. Now, once I reduce this to the new alphabet S double prime, this new alphabet S double prime will have 3 letters, and again you sort out this 3 letters in a descending order to obtain the table 1.3. So, I get a table, this is the reduced 3 letter alphabet S2, S3 prime, S1. This order has changed because S1 probability is lower than S3 prime. So, we have changed the order, and this we continue with this S3 prime. The code word based on the previous discussion would be alpha 2. Now, again in this case the 2 least probable symbols are S1 and S3 prime. So, both of this will differ only in the last bit. So, let us assume that SC S3 prime is alpha 3 concate with 0 and code word for S1 would be alpha 3 concate with 1, but we already know that the code word for S3 prime is equal to alpha 2. So, if you substitute alpha 2 is equal to alpha 3 concate 0 and go back and substitute, you will find you will get this result, code word for S3, code word for S4 and code word for S5. Now, we have reached to a stage where we have the alphabet of size 3. Now, we have to go to one more step of reduction. Finally, we combine these 2 symbols in this reduced 3 letter alphabet to get the reduced 2 letter alphabet, and we combine S3 prime and S1 prime to get S3 double prime. So, what we do is that again we define a new alphabet, this time with only 2 letters S3 prime and S2. S2 remains intact from the previous reduced 3 letter alphabet, but S3 prime is composed of the letters S3 double prime is composed of the letter S3 prime and S1, and the probability for S3 double prime will be equal to probability of S3 prime plus probability of S1, that turns out to be 0.6. So, now we have finally a source alphabet consisting of only 2 letters, that is S3 prime, S2, arrange them in the decreasing order. If I do that, I get 0.6 and 0.4, and we know that for S3 prime the code word is alpha 3, and for S2 we have CS2. Now, since there are only 2 letters in this finally reduced 2 letter alphabet, the code word assignment is straightforward. We assign CS3 double prime as 0 and CS2 equal to 1. So, CS2 is equal to 1, CS3 double prime is equal to 0, which means that alpha 3, because CS3 prime is alpha 3, which means alpha 3 is equal to 0, and since we have solved for alpha 3, we know alpha 2, we know alpha 1, we can go back and resubstitute for the code words, and finally what we get is this. So, to complete, C of S2 is equal to 1. So, this is how we generate the code words for the source S based on the Huffman coding procedure, and this procedure can be summarized as shown in the figure below. So, to start with, I order the source symbols in a decreasing order 0.4, 0.2, I combine these two, I get a new source symbol, arrange them in a decreasing order again, I do not change, I have kept it here, combine these two because they are in the bottom most of the sorted list, I combine them, I get probability equal to 0.4, 0.4 I move it above S1, so I get a new alphabet of a reduced size, that is 3 letters, I move it up here, I get this, and finally I combine this two and I get S3 double prime 0.6, 0.4. And now this is the basically this whole procedure, what we have done for the Huffman coding gets summarized in this figure, and now you can calculate the length, that is the average length for this code as 0.4 multiplied by 1 because S2 is of length 1, and what I get is 2.2 bits per symbol. Now if you calculate the efficiency for this, it turns out to be HS by L, you can find out it will be very close to 1. There is another parameter for codes which is defined as a redundancy of a code, and that by definition is equal to HS minus L, and if we use the parameter of redundancy to define the efficiency or to define the compactness of a code, then this redundancy for this code which we have designed comes out to be 0.078 bits per symbol, and ideally this value is expected to be as close as possible to 0. So with this we have seen how to design a compact code based on Huffman coding procedures, and this Huffman coding procedure was based on some simple observations for design of compact codes. Now this same Huffman coding procedure can also be looked from the point of view of tree structure, and we will talk about this in our next class.